Yes. The question is, of course, if you once you start moving to non-comparison based models, what happens? And I'm not getting into here because even sorting you can do faster in non-comparison based models, and so that's so obviously you could be able to do it here. But working on KMP, which is strictly comparison based, there is no way that you could do that in any comparison algorithm any way faster. If you want to start being smart and use all kinds of number theory, then it's possible that you can do it faster than n log n, although you would probably still not be able to do it in strictly linear time, unless your alphabet is very, yes, it's a polynomial. Okay, so now we're going back to scaled pattern matching. Now, just to remind you of something that we've seen before, the motivation here is we're searching for templates in aerial photographs. So you have an aerial photo, you have a template, you want to find all the locations, you remember this picture, you rotate it, you scale it, the scale matches, you found it. The model is a low-level model. In other words, we're looking at a pixel level. And the point is that although computer vision people do not usually work at the pixel level, they generally either do Huff transforms or all kinds of things. They don't work, or they do a geometric redrawing of the scenes. But if you want to avoid costly processing, suppose, for example, that you're working on in a movie or a lot of pictures one after another, you don't want to start processing every picture. So whatever you can do at a pixel level, you're going to be able to do even if you have a lot of them. And we're looking for asymptotically efficient solutions. And we're looking for serial exact algorithms. So that's the models that we've been working on until now, because we are doing combinatorial models. Now, the types of approximations we spoke about, where you can look at local errors that are levels of details, occlusion, or noise. We saw already how you can find it with mismatches in time n squared log m, because in fact, for binary or for fixed alphabets, because in fact you can serialize and do FFT. So this time we saw edit distance and all these other things we haven't seen yet. I think we're going to see them within a couple of days. Well, we don't have more than a few days, but we'll see them. Now for orientation, in other words, the rotations, there was a result by Fredrickson and Ukkonen that showed how to do that in time n squared m to the fifth, find every pattern in the text in time n squared m to the fifth. And we're going to see here an algorithm from a few years after that that shows how to do it in time n squared m to the third. Now, for scaling, and that's what we're concentrating on now, the question is this. First of all, you may be talking about natural scales. Natural scales mean you scale something to twice as big, 3 times as big, 4 times as big, not 1.33 times as big. So if you're talking about natural scales, in one dimension, this and a bunch of other things were shown by Eilam Tzoref and Vishkin to be done in linear time. For 2 dimensions, Gadi Landau and I and Uzi Vishkin showed how to do it in time O of n squared log sigma, where sigma is the size of the alphabet. And finally, with Gruya Kalinescu in 2000, we showed how to do it in time O of n squared without the log sigma, and for dictionary matching. But what I'm going to show now is something else. I want to talk about not natural scales, but rather real scales. In other words, I really am scaling something to 1.356. How can I find it? Yeah, we know that it seems daunting, but it can be done. But the thing is, the problem is inherently inexact. So in some sense, for combinatorists to look at this problem seems like almost forget it, because what's a half a pixel? If I make an occurrence 1.5 times bigger, it means that some pixel now, that something may grow up, something that was 1 pixel long is now 1.5 pixels. How do I do that? So again, when computer vision guys, they integrate and they do all these things that are inexact. But combinatorists who deal with exact matching, what is a half a pixel as far as we're concerned? So that's why the solutions until this paper, which we're going to see now, all dealt with natural scales because you didn't have half pixels. So you had the scales that you were looking at is 1, 2, 3, 4, 5, only natural numbers. And so if we look at the problem in a natural scale, that's easy to define. You have an n by n text and an m by m pattern, and you want to find the pattern in the text in all discrete sizes. So for example, if this was your pattern, you say, well, the pattern occurs here in size 1. It occurs here in size 2, because every pixel becomes a 2 by 2 pixel. And it occurs here in size 3. So, of course, yeah, there's also a size 2 here. And of course, things can overlap, but these would be the locations that we want to find. Now, this in itself seems like a hard thing, because obviously, you can take your pattern, scale it to 2, to 3, to 4, and do a 2D matching like we know how to do. But then, your time is going to be linear times the number of scales. In other words, linear times n divided by m, which is going to be the number of times you have to look at. And you don't want to do that. So the idea, okay, so this shows what it means to be scaled by 3. You just take every pixel as a 3 by 3. But the idea for the algorithms that actually did that in linear time was the following. If you fix a scale, okay, let's now fix a scale, divide the text into these S by S rectangles, squares. Now we're going to show that for each one of these squares, that's also called an S block, for each one of them, you can do a constant amount of time and decide what scales it can be good for. And decide if it can be good for this particular scale. So in constant time, we work on each of these S blocks. And then, so the time for finding all the occurrences in scale S is going to be the number of S blocks. It's not going to be n. And since there's only n squared divided by s squared S blocks, the total time is going to be, where the scale goes from 1 to n over m, n squared divided by 1 over s squared. If you take the n squared out, the sum of 1 over s squared, where s goes from 1 to whatever, converges to a constant. So therefore, your total time is linear. So all the ideas around the algorithms that worked in linear time for scaling, this is what they did. They said, okay, there are all kinds of fancy methods to work constant time on every S block. But the problem was with real scales. And that problem had been open even for strings. Eventually, and this we're not going to get to this time because I'm not staying here past Thursday. So at least this time we're not going to see this. But there has been work done. Eventually, we even figured out how to do real scales for 2 dimensions, and there's some nifty stuff there. But when this particular paper was written, there was not even a good definition, where people who work in a discrete model can look at real scales. So we said, let's look at real scaled for strings and try to find a reasonable discrete model for the strings. And this is the definition that we came up with. So suppose that this is your string. and you want to scale it to 2. So we know how to scale it to 2. We take every symbol and we double it. So this A becomes 2 A's, this A becomes 2 A's, the B becomes 2 B's. Each one of the C's become 2, so we have 1, 2, 3, 4, 5, 6 B's, 6 C's, and then the 2 B's become 4 B's. That's scaled to 2. That's easy. We know how to do that. But if we want to scale it to 1.5, what are we going to do? Well, 1.5 times 2 is 3. That's good. 1.5 times 1 is 1.5. So let's truncate. You can also, what I'm going to show you now is going to assume truncation because that's easy. But it also, the same algorithm also works for, how do you call it? When you go, yes, if it's like over the half, you go up, and how do you call it? Yes, rounding, right? So it would work for rounding also, not just for truncation. But for simplicity, let's now just consider truncation. So we now have a well-defined meaning of non-natural scales. Yes? You look at your runs, and as long as you multiply by that number, the number of runs, if it's good, it's good. And whatever not, you're going to truncate the half pixel or quarter or whatever it is. Well, when I say real, I actually assume real, and I'm going to show that it's real. Now, obviously, in reality, it's rational, but the algorithm we're going to see is going to work for real. Now, how do you do real numbers in a computer is another story, but everything that I'm going to show, in fact, all the theory behind it is going to give us a real, it's going to give us all the real numbers that you can actually scale to. Now, this particular definition is not good for 2 dimensions because things don't align. Since you may be truncating in one row, and then the next row you'll be truncating differently, and things aren't going to align. So we knew that this definition is bad for 2 dimensions. At the end, the definition we had for 2 dimensions was a different one, but we did manage to discretize it. And in fact, not only did we manage to discretize the definition, but I accomplished something that has always been a dream of mine. And that is, I used Lemma in one of my papers. Now, did any of you ever hear of Lemma? Okay, so Lemma is a picture of a face of a girl with a florid hat that is a benchmark in computer vision. So computer vision from the very early days, whenever they want to prove some new algorithm or something, that's the benchmark. They do it on Lemma. So I said, how am I going to be able to use Lemma in one of my algorithms? Now, there's a story about this Lemma also, because the first computer vision people, hackers are hackers, okay? So there were a bunch of hackers that were working in, I think it was in California somewhere, and they were working on computer vision, and they came up with some algorithm, and they figured, yeah, we can do this. Let's find something to run it on. Now, so they were looking for some images in the lab. Now, what images did they have in the lab? Obviously, they had the manuals and all the technical stuff. As far as food, they had pizza and some beer. And the pizza was already stale and the beer was flat, but it doesn't matter. I mean, that's what hackers do. And then, as far as any pictures that they had, so there was a Playboy magazine that was there. So they opened up the centerfold, and the centerfold of Playboy on that month, or was it the month before? I don't know. These hackers may have not been up to date. But the centerfold was a model called Lemma, and they had her picture. Now, for decency's sake, they only used the head. So Lemma is cut here. She has the head. You don't have the full picture of Lemma. And that was used by them, and then it became a benchmark. And Lemma has been used in maybe hundreds of thousands by now of papers in computer vision as a benchmark. Now, it turns out, the story is a bit interesting because Playboy is very, very, very uh, uh, insistent on their copyrights. So the fact that Lena is being used willy-nilly without getting permission from Playboy, in fact, is a problem. But Playboy magnanimously came out with a decree and saying that we realize that this is important to science. So Playboy's contribution to science is that we allow a free use of Lena for scientific purposes. So Lena can be used freely for scientific purposes. Now, the cycle was closed because in about 15 years ago, I think, or 10 years ago, or something like that. But at least a decade ago, there was a 50-year of one of the major computer vision conferences. It was the 50-year occurrence of that conference. And so the conference organizers decided, let's bring Lena over to the conference. So they started looking all over the world, and they found her. And Lena, she moved back to Scandinavia. She was Scandinavian. She came to America for a job. She became famous in computer vision society, but she didn't even know about it. So she went back to Scandinavia. She got married and had children, and she was at that time already a grandmother when they found her. And they told her, listen, you know, you are the benchmark in computer vision. She was very excited. They flew her over to the conference, and she was meeting people and saying hello, this nice grandmother. So that was Lena. That was the story of Lena. Now, to me, when we finally defined matching in a discrete way, scaling in a discrete way, then I said, good. Now I've got to check this on Lena. So I grabbed one of my grad students. I said, take a picture of Lena and scale it up according to our definition. And let's see how it looks, if it's going to look pixelated or not. So she did. And so in my paper, we give the definition, and then we show, look, the definition actually works even in the real world, because we see Lena in all kinds of sizes according to our definition without the sinus waves and everything that the graphics people use. So we showed that actually this works even in a discrete fashion for scaling, and then we moved on and showed our algorithm. So I managed to fulfill a lifelong goal and use Lena in a theoretical paper in pattern matching. And I believe that is still a record. I don't know of any other paper in pattern matching that uses Lena except for that one. So that was it. But to get back, let's forget the nostalgia here. To get back to our task. So this is how we define scaling for one dimension. We're talking here about a string, so we don't mind truncating because we don't need to align. Everything's good. And this is our definition. So what we want to do is, given a string, find out, and given a text, find out if there is any real number that if we multiply the string by and truncate it, we would get something in the text that is equivalent to that. And we want to do that as fast as possible. And surprisingly enough, we will be able to do this in linear time. So let's move on now. So formally, what are we talking about? So first of all, for how we're going to write things down. When I'm going, as you noticed already, so the fact that something occurs many times one after the other, so I can add up their residuals, so I may get more, less to truncate. So for example, where is it useful? I saw yesterday in Ahmedabad, for example, that for 5 rupees, people either truncate or round. It depends on if you're buying or selling. I mean, if they're selling to you, they round up. But if you buy, of course, you want to truncate. But that's the idea. But the thing is, suppose you buy 2 things, each one has 5 rupees. At that point, you don't need to truncate or round because you add them up. And now you get 10 rupees, and that's already considered something that people are willing to handle and not just take from you. So, okay. So this is why when I have A appearing one after another R times, then I'm going to just write A to the R. So here's my problem definition now. My input is pattern matching. I have a pattern, P equals A1 R1, A2 R2 up to AJ Rj, where the length of the pattern is M, and I have a text of length N. And what I want to do is output all the text locations where the text looks like A1 to the C1, A2 to the floor of alpha times R2 up to AJ minus 1, the floor of alpha times Rj minus 1, and AJ Cj for some alpha greater than or equal to 1, real, where the C's, C1 is greater than or equal to the floor of alpha times R, alpha times R1, and Cj is greater than or equal to alpha times the floor of R times J. Now, what does this mean? So it means the following. If I had a pattern that's A, B, 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 C, 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 B, D, okay? Now, I'm going to blow this pattern up. So according to the definition, what I want is, so B gets blown up to this, and C gets blown up appropriately to the number of C's, and so does the other B, and the two A's get blown up to A's. But what happens if there are more A's here in the text? Well, in pattern matching, we never worried about the fact that there may be more things there, right? So this should still be okay. In other words, even if in the text we have A to the C1, where C1 is greater than what I need in order to accommodate my A's, I'm still okay. So we don't worry, the borders don't have to be strict. In pattern matching also, if I'm looking for A, B, C in a text, and if there was an A here and a C here, I'm not saying, well, I'm not going to be able to see the border of this A, right? When we were kids, there was this stupid joke that everybody used to say, you want to see what a great artist I am? Look at this. You see what I drew? They show you a white page. Say, what? You didn't draw anything. Says, nah, I drew a polar bear hiding in the snow. So you can't see the edges. You probably have like similar kinds of things. Then they show you a black page. I drew a black bear hiding in the dark. I mean, a black bear at night or whatever. I mean, any kind of stupid thing like that. But this is what we have. Yeah, you have something like that also, some joke with Indian kids? No? They have other stupid jokes, I assume. Yeah, I mean, kids have jokes. So we don't care that there are A's before that, and it's like, this is white and this is white, and you don't see the bear. We don't care. I mean, the bear is there. So this is the definition here. Well, yes, those A's that are not in the right size are not part of the match, but I would say that in the text, at this place, there is a match. However, and in some sense, I want to use, though, the clear distinctness, which is why I come up for my algorithm, which is why I come up with an alternate definition. But wait, before the alternate definition, let's say this remark, because it's a philosophical remark. Okay, so as you saw, when we defined the scaling, we said alpha is greater than or equal to 1. It means that basically we're scaling the pattern up. We're looking for all the locations of the pattern where it's bigger, not where it's smaller. So we're not scaling down, we're scaling up. And the problem was that we wanted to avoid a lot of conceptual problems, and loss of resolution is one of them, because philosophically we didn't even want to get into it. I mean, philosophically, if you take alpha less than 1 over m, then everything converges to a single pixel. And so you move far enough away and everything looks the same. And so scaling down, we said, has problems of its own. Let's not worry about it. Let's worry about scaling up, which means let's assume that I have my picture at the lowest resolution that I can afford to actually see it. And now I'm going to scale it up and see if it appears in bigger forms. So that's why we didn't want to look at Ks that are too tiny. Ks that are too tiny. So you'll say I match everywhere. So what's the... All right. So, but our other definition 2 actually simplifies it. It says that I want in the text to actually see exactly a1 to the floor of alpha times r1, a2 to the floor of alpha times. So the symbol that's here is in fact a different symbol, and the symbol that's here is in fact a different symbol. So we don't want any of these jokes about the white bears in the snow. All right? So let's see the example here and understand. So if this is our pattern, AAB, CCC, BBB. Okay, so a to the 3.5. So if 3.5 or 3 over 2, sorry. If 1.5 is my alpha, so 1.5 times 2 is 3, 1.5 times b is b, 1.5 times 3 here is 4 c's, etc. So this is what we get. And according to definition 2, if this was a D and this was an E, then I have a match. According to definition 1, I have a match here also, but not definition 2. Because definition 2 would not see here 3.5 times 4, because it's not. It's more than that. It's not the floor of that. Okay? So obviously definition 1 is the one that you want to do, and not definition 2. But definition 2 is the one that we have a good algorithm for. So what do? We prove that if you know how to do definition 2, you can do definition 1 also, and then proceed to do definition 2. So that's what we're going to do. Not yet. I am doing scaled, but we'll see all of a sudden parameterized matching will rear its head, like you see these cobras when they come out of the basket. So parameterized matching will show up. Okay, so the first thing we need to do is to show that the definitions are equivalent, and then we can willy-nilly just do definition 2 and forget about the complexities of definition 1. And why? Okay, so the first thing we do is we're going to split the text and the pattern to what we call the symbol part and the length part. Because in some sense, there's two things going on here. As you saw, when I write a to the r, a is a symbol, r is a number, so which is the length of the run of how many a's I have. So we'll call the symbol text ts, the symbol pattern ps, and the length text tl, and the length pattern pl. So that's what we're going to do. So here is an example. If this is the pattern AAB, this is the pattern that we have. So what is the symbol part? We have an A, a B, a C, and a B. So this would be the pattern, the symbol pattern. And the length pattern is going to be 2, 1, 3, 4. So that's just the length of the runs. So we split this thing into 2. Now, if we're going to look at this particular scary text, so again, we have a D, then we have a bunch of A's, then we have a B and C, then a B again, and the B is very long, but then there's an E. So this is the symbol text. But the length text is this. So when we're looking for a matching, what we really want to do is find a place where the symbols match, and then where the lengths actually are a multiple, an appropriate multiple according to our definition. So the time for this split to rewrite it is obviously n plus m, because that's easy. And to find the pattern, the symbol pattern in the symbol text is O of n plus m, and we know many ways of doing it. So the hard part is just finding PL in TL. So that's really the only problem that we're now looking at. So now we forget all about Lemma and images and pixels and we're blowing up and blowing down. And all we have is a little problem in numbers. There's a little number algorithm that we're looking for. And that is when we have a bunch of numbers. Our pattern is a bunch of numbers. Our text is a bunch of numbers. And we want to find out whether there exists some alpha such that the floor of alpha times our numbers in the pattern is equal to the text by definition 1 or by definition 2. And so that's the only thing we need to do. And what we need to do is show that if we can solve definition 2 in time O of Fn, then we can solve definition 1 in time O of Fn, because definition 1 is actually the more complex definition. So if you can do definition 1 in whatever time it takes, you can always do definition 2. So, but we're going to show definition 2. So that's what we're going to show, that we can solve 1. Why? Because, okay, forget about the first and the last symbol, because the first and the last symbols are the ones where you may have trouble. So throw them away. Just look at the middle of your thing, at this part. And in time O of Fn, find it, because this is definition 2. I mean, the center has to appear exactly, because it has the first and the last symbols stuck on the sides. So we can do definition 2. So you find all the places where you have definition 2. Obviously, for each match, you don't know what's the beginning and the end, but fine. So go for each match that you found, and there's not going to be more than O of n matches, obviously, but for each match, do O of 1 time, just taking a look at the first and the last numbers on the sides, whether they're okay, whether they're greater than or equal to your alpha. I mean, you can figure out the alpha by division, and then once you know the alpha, multiply it by the first number, truncate, and see if you're longer or not. Do that for the last number too. So it's O of 1, no problem. So now, from now on, so our time, total time, is obviously O of Fn plus n. We didn't even presume that we can do it in less than O of n times, so the total is O of Fn. Good, so now we're going to forget definition 1, and we're just going to do definition 2. Because we know that we can always go back to 1. Yes. Yes, there are. But we're only going to do definition 2 from the second part on. So in fact, we're going to get definition 1, because look what happens. Yes, I truncate the sides. So there's the first, the second, the third one, and then the last one, okay? Now, definition 1 also expects these guys to be exact. It's here that you have the play. So we're going to look only for this, and we're going to then find every location where this happens. Now, for every such location, we figure out how much there is the text, how much in the pattern, we divide them, and then we multiply and see whether it would work for here also. And the same thing for the other side. Yes, we do definition 2, but from the second place on to the j minus 1 place. Yes, obviously I couldn't do it for the first. That's very easy. Then look for the first, look for the second, and see all the places that they match. Yeah. You have 2 numbers, okay? So finding 2 numbers, go for every place where you have the first number, see, divide it, see your alpha, then divide the second one and see if it's the same. The one next to it, and do the same for every pair. Fine. So take the smaller of the two ratios and see if it follows. Okay. I mean, 2 is never a problem. Okay, so we showed this. So here's the naive algorithm for matching PL and TL. For every text location, then okay, no, so we're now talking only about PL and TL, right? Because in general, what you're going to do is run KMP, find all the places. Now you want to find TL and PL according to definition 2, and all the places where you found that PL matches TL in definition 2. And also there is a match of PS and TS, that would be a match. So that's what we're going to do. So at this point, we're forgetting all about everything else, and all we need to do is match the pattern length in the text where the match is exact. Okay, so for each text location, and we're doing the naive algorithm because, as I told you before, whenever we're encountering a problem, the first thing to do, see how can I solve it in a naive way, and then start improving. And this is exactly what we're going to do here. We're going to improve and improve and improve and improve until finally we get to linear time. But we start with this. For each text location, put the pattern starting in that location, and calculate the interval of alphas that would be good for that for that text pattern pair. Okay, that's the interval of the possible scales. So, for example, if I have, we're now dealing with numbers. So I have numbers for the pattern. So let's say I have 2, 5, 10, and I have numbers for the text. So this is the pattern, and then there's a text. I have 10, 20, 30. So when I'm saying, what would be the alphas that are relevant for this pattern to actually match in this text? And so my claim is that the alphas that we're talking about are going to be between, it's a closed segment on one side and an open segment on the other side, but it's going to be between the text divided by the pattern here and the text plus 1 divided by the pattern, but open. Any alpha in that segment is going to be a possible scale if I want this P to match in this T. And why is that? Because if I take T, that's the left side, right? T divided by P. If I take T divided by P and I multiply it by P, then I get the text. So that's very good. But any alpha that is less than T divided by P, already alpha times P, if you take the floor, is going to be less than T, so it's not going to match. So T divided by P, if I multiply it by the pattern, yes, it's going to match that text. Anything less than that, even a tiny bit, even an epsilon, is already bad. But this itself is good, which is why it's a closed segment on the left. But it's an open segment on the right. Why? Because T plus 1 divided by P times P is actually equal to T plus 1. And T plus 1 is greater than what is written here, whether you truncate or you don't truncate. But even an epsilon less than that, because we're truncating, then it's going to match. So that's why T plus 1 divided by P is the border on the right, but you never reach that, because reaching that is already bad. No matter how close you get to it is good, which is why it's an open segment. Okay, so what this segment defined is the real numbers, and it's really real numbers because of this open segment. So I write it using rational numbers, but I'm defining real numbers here. So it gives us the range of real numbers that all could have been okay for scaling the pattern if the pattern started here and ended here. But we do that also for the second one. So we do here 20 divided by 5 is 4. 21 divided by 5 is 4, and 1 over and 1 over 5 or something. Okay, so this is this, but the segment that I got here was 10 divided by 2 is 5, and then 11 divided by 2 is whatever it is, but you can see that the intersection between these two segments is empty. And so I don't have a pattern occurrence starting here because these two segments don't intersect. So it couldn't, there's no common real number that if we multiply this by the real number and this by the real number and truncate, we're going to get the text. So that is already bad. So this gives us the algorithm. Yes. So for every text location, I'm going to compute the intervals and look for the intersection. So the time is O of nm. So only if the intersection of all the intervals is not empty, then I know that there's a match. But the time is O of nm. It's not awful. I mean, initially you would think, well, how do I even do it? But the naive way, O of nm. So let's look at this example. If the pattern is 2, 1, 2, 3, 2, and the text is that, so if we're going to compute the first interval, it's 1 and 3/2. The second interval is 4 and 5. And so we see already that the intersection is empty, so we move on to the next. So we shift and we do the same thing. So we compute the first interval, and we get 2 and 5 over 2. The second interval is 2, 3. The next interval is 4 divided by 2 is 2, and 5 divided by 2 is 5/2. Then we get 7 divided by 3, 8 divided by 3. And finally, the last interval is 2. 4 divided by 2 is 2, and then 5/2. So these are our intervals for the second location. And then we're going to take every single one of these and check the intersection. And it turns out that the intersection 7 over 3, 5/2 actually appears in all of them. So yes, so there is a scaled matching in location 2. And any real number greater than 7 over 3 and less than 5/2 would be a good scaling factor. Okay, so that's a naive algorithm. It's very simple. It's very nice. Yes. So yeah, if you're running this, you're going to make a lot of shortcuts. First, you'll run the KMP and find the places, and then only go there, because why work for nothing? Yes. But suppose that you have a binary alphabet and everything is going to be then 0, 1, 0, 1, 0, 1. Then in every location, or in every second location, it's going to work. So it's not going to necessarily help you in a symptotic way. Yes. So that's also easy. And these are, at least the sides of every intersection are rational numbers. So that's all can be done in O of one time. Okay, now comes the improvement. And what we're going to use for the improvement is parameterized matching. Now you say, where did parameterized matching come from? All right, that's what's beautiful about this. I can become David Copperfield. So I'm not going to tell you what parameterized matching is because I just did. But what I do need to tell you is to remember that what we know is that for sigma that can be sorted in linear time, such as, for example, 1 through n, parameterized matching can be done in time O of n. And in our case, of course it can, because all the numbers are between 1 and n. So we can do parameterized matching in linear time here. But how is that going to help us? Okay, So here comes the key lemma that is going to help us do this. So the lemma says that there exists a real alpha greater than or equal to 1 for which PL matches TL at location I. In other words, by the scaled matching, scaled to alpha, only if PL parameterized matches TL at I. So in other words, if it doesn't parameterize match, it's not going to scale. If it parameterized matches, maybe yes, maybe no, but certainly all the places that don't parameterize matches aren't going to scale. So that's what we need to prove. So here's the proof. Let's assume that PL does not parameterize match at location I. Okay, so we assume to the contrary. And the question is, can it actually scale match to alpha, to some alpha? Is there an alpha such that it scaled matches? So let's see. There are only two possible situations that we need to look at when it doesn't parameterize match. One situation is where the same element in the pattern matches two different elements in the text. And the other one is when the same element in the text matches more than one element in the pattern. So let's start with case 1. So we have a B in the pattern. We have in the text an A matching B, but here there is a C that's not equal to A and it matches B. So obviously, let's assume that this was the bigger of the two. It doesn't really matter. If it's not, we do the same kind of argument, but the other side. And because it doesn't match, so and because we're talking about numbers, and since we're assuming that C is greater than A, then C is greater than or equal to A plus 1. It can be a lot bigger than that, but it's at least A plus 1. Okay, so now let's compute the intervals. So here we get A over B and A plus 1 over B. And here we get, for the smallest possible C, A plus 1 over B and A plus 2 over B. Now you can see right away that for the smallest possible C, already these two intervals are distinct because this is an open interval and this is closed. So in fact, the intersection between these two intervals is empty. And as you make C any bigger, this is going to go even further away. So there is no way that there's going to be any alpha that you can match. So that would be the easy case, the case where the pattern has two B's, where the same element in the pattern matches two different elements in the text, and that's why there was no parameterized matching. The other possibility that there's no parameterized matching is if the same element in the text match two different elements in the pattern. That's the other side. If none of these occur, then there is a parameterized matching. But if this happens, and again, let's assume that the C is greater than or equal to B plus 1, then let's see. What is the segment here? It's A over B to A plus 1 over B. And the segment here is A over B plus 1 and A plus 1 over B plus 1. Okay, so what can we say here? A over B plus 1 is obviously smaller than A over B, because if you increase the denominator, you're going to get a smaller fraction, right? So it means that this segment starts to the left of this segment. Okay? Now, the question is, if there's an intersection that is not empty, it means that this side actually falls here. So what it means is that A plus 1 over B plus 1 has to be greater than A over B. So if A plus 1 over B plus 1 is strictly greater than A over B, then that's what we get. So let's see what happens. So A plus 1 over B plus 1 is strictly greater than A over B. And now let's multiply the two sides, and what we get is that A plus B is greater than AB plus A. Subtract the AB from both sides, and you get that B is greater than A. Okay? So if B is greater than A, the intersection is not empty. But what does it mean that B is greater than A? B is greater than A. This is the text, this is the pattern. It means that we scale down. And we said we're not scaling down. Scaling down, everything matches. We don't do that. That doesn't make sense. So that can't happen either. So for our case, when we're scaling up, it has to be the case that only if we can do a parameterized match, we have a scaled matching. And otherwise, there isn't. So here's now our algorithm for real scaled string matching. P1, let P1, PI1, PI2 to PIJ be the different numbers in PL. Okay, because now that we have the parameterized matching, we don't really need to check every segment. We only need to check segments of different numbers because they're going to be the same in the text and in the pattern if there's going to be a scaled matching. So that already kind of cuts it down to the different numbers that we have. So P1 through Pij are the different numbers. We parameterized match PL and TL, and then for each match we're going to check the intersection only of Pi1, Pij, and the corresponding symbols in TL. So the same algorithm as before, but rather than check every number, we only check those that parameterize match. So let's look again at how this thing looks. So here's the example. Suppose we have 2, 3, 2, 3, 2. We only have two different elements, 2 and 3. Okay, so what are the parameterized matches of 2, 3, 2, 3, 2? We have one here, we have one here, we have one here, and we have one there. Because what we need, anything that has 5 elements that alternate is going to be a parameterized match. So these 5, this doesn't, these 5, and this 5. But anything in between, no, because you already have 3 different letters, so that wouldn't be right. So we only have 4 places that parameterize match. But let's check in these 4 places what happens. So let's start here. 5 over 2 and 6 over 2 is 2.5, 3. And then the next one is 6 over 3, which is 2. And then 7 over 3, which is 2 1/3. And you can see that the intersection here is empty. So already we discard this particular option just by checking those 2. No more. The second one, we do 6 over 2. 6 over 2 and 7 over 2 gives us 3 and 3.5. And then 5 over 3 is 1 2/3, and 6 over 3 is 2. So here also the intersection is empty. So there's no match here. Here in this one, 10 over 2 is 5. 11 over 2 is 5.5. 6 over 3 is 2. And 7 over 3 is 2 1/3. Again, the intersection is empty. So we discard this one. But here, we get 6 over 2 is 3, and then 7 over 2 is 3.5. 10 over 3 is 3 1/3, and 11 over 3 is 3 2/3. So here, between 3 1/3 and 3 1/2, we have an intersection, so that's our scale. So we found the scale match. Question is, did we gain anything from this? And the answer is yes. And look at the miracle that happened here, just by doing the parameterized matching. Because the sum of the PIKs can't be greater than M. Because what are these PIKs, right? These are really runs. All the runs together are going to be M. The different runs are a subset of all the runs. So clearly, the sum of all the different runs is less than or equal to M. But if that's the case, there are only O of square root of M different such runs, different such PIs. So we have O of N time for the parameterized matching, and we have O of square root of M verification time for each location. So already the total time went down from O of nm to O of n square root of m. Aha! So now we're rubbing our hands in glee and saying, what else can we do? Well, what else we can do is analyze a little bit better, because the one thing that we haven't taken into account is how many places do we parameterize match? If we parameterize match in few places, then it's not going to be n times square root of m. It's going to be less. So the next thing that we need to do is work out how many times do we parameterize match. Now, do you want to break here and we'll continue after the break, or just shove on and I can go on talking for an hour and finish, but the question is, do people feel like they need to drink something? I have been drinking all the time as I talk. Okay. Saw was that if at every location where we have a parameterized match, we only have to check the segments for the different segments in every pattern, at that point, we obviously only have n times square root of m, because we can't have more than square root of m different segments. But different run lengths. But what we said is that we still have not utilized the fact that maybe just the parameterized matching part is already going to thin out the locations in the text, and we may not really need to check that square root of m in every text location. Maybe we need to check less text locations. Now, again, notice that in that we said if everything is different, if all the numbers are different, then we can have a different, then we can have a parameterized match in every location. But remember that in our case, we can't have everybody different because these things are runs. So we only have square root of m different options to begin with. So there is a hope that we can do something. And this hope we get here. Because what we're going to try to do now is really find some upper bound on the number of possible parameterized matches. That's our hope. And in fact, the following lemma, which we're going to prove, is going to do just what we want. Because what this lemma says is that if the pattern length is m, the text length is n, and let's say that we have j different numbers in the pattern. So this is the situation that we have. Then what we're going to show is that there are at most n over 2j parameterized matches of PL in TL. Okay, now, this is beautiful, because if this is what we can show, the verification time for every one of these positions is going to be j, because that's what we have. So if there are only n over 2j locations that we have to verify, n over 2j times j is O of n. So then we are down to a truly linear time algorithm for real scaled matching. So that's pretty awesome. And so let's see now how we prove the lemma, which is not that difficult, and at that we'll finish this algorithm. Okay, so what is happening here? So let's assume that this is our pattern, and those are the locations pi1 through pij. These are the locations of our different p's, of the different p's. Each one of them is different from another. And we have a parameterized match, which means that pi1 matches dA1, pi2 matches dA2, and pij matches dAj. Now, in the text, these guys are also numbers of run lengths, because that's how we build this is the text length. So our pattern and the text, we're talking about the length parts of them. So these are also lengths, and these are also all different, A1, A2, and AJ. So in fact, if we sum all of them up, what we're going to get is that the sum of these A's that match the pattern are greater than or equal to j squared over 2, because the least that it can be is that these are the numbers 1, 2, 3, 4, 5 up to j. They could be a lot more than that. But even if that's what they are, then the sum of that is j squared over 2. So we are greater than that. All right. So let's now say that x is the total number of parameterized matches in the text. So let's add all the text elements that matched the those first occurrences of the PIs, of the PIJs, of the PIKs. Okay, so for every pattern, for every parameterized match, we have all of these guys. Okay, let's add them all up. So the total sum is going to be, if there are x parameterized matching, the total sum is going to have to be greater than x times j squared over 2. But there may be overlaps, so we may be counting things here more than once. What I want to do is, in order to find what x is, I want to count these things only once each. So I don't want for some x to count the same ai, and then that same ai is for another x, and the same ai is for another x. So that's, I want to get rid of these overlaps. So let's see how many overlaps we can have. Okay, so the point is this. For every text location that we are counting, there can't be more than j matches that count it, because why are we counting it? Because actually it corresponds to the first occurrence of one of the p's. Let's go back to the picture and you'll be able to see what's happening. So who is going to count this one? Well, if there's a parameterized match over here, it's going to be counted because it's pi2. Well, it may also be counted if pi1 is here. So it may be counted for pi1, and it may be counted for pij if pij is here. But those are the only locations where it's going to be counted. In the entire m options of shifting the pattern over this A2, only j could count it more than once. So that's also an upper bound. So the most that we can count it is j times. So every such text location, at most j matches counted. So therefore, the total count without overlap has to be greater than xj over 2 times 1 over j. I mean, if it's less than people, then we get even a bigger number. But that's the smallest number that can be as far as the total is concerned. So what we have, the total count without the overlaps, is going to have to be greater than this, which the 1j actually we can cancel out. So we get xj over 2. So therefore, xj over 2 is the smallest number that we can get for this total count. And in fact, it could be better. But this xj over 2, whatever it is, has to be less than or equal to n. Because at this point, we didn't count anything twice. And if we counted every single element in the TL and added them all up, we'll get n. Because that's how TL came about. So if xj over 2 is less than or equal to n, it means that x is less than or equal to 2n divided by j. And if x is equal to 2n divided by j, then the number of times that we actually do compute those segments is going to be 2n divided by j times j. So here it is. It's O of n. So what we saw is that you can get a very nice linear time algorithm. But how do we get it? First, we look at the naive algorithm. Then we say, OK, do we have any tool that can make the naive algorithm work faster? And tool number one that we had was parameterized matching, because what it says is we now don't need to check every position. So we only check those that are different from each other. That already made it smaller. And then we haven't really even changed the algorithm. So the same algorithm that we said the time is O of n square root of m, Really, that wasn't the time. The same algorithm, we didn't even change it. We just changed the analysis and we tightened it. We said, okay, there was something else happening here that we haven't used. However, the thing to remember is that this algorithm is linear time as an algorithm for scaled matching. But if I ask you to find the one-dimensional linear time algorithm in run-length compressed text, in other words, here is the problem. So the problem is that the text is already compressed. There is no n and m that we can use as crutches, but rather the text is given, the pattern is given, these are numbers, and I want you to find the solution. Can you do that in time that is faster than O of nm? Because that doesn't seem like we can do it. The only reason we could do it is because nm were not the real length of the text and the pattern that we were working with. If you're looking for, then if the number is not a representative of something long, in some sense what we said was we are given a text and a pattern whose numbers are represented in unary notation. And so that made it easy. But what if the numbers are represented not in unary notation but in binary notation? Can we then do faster? I don't know. So this is an open problem. Again, if anyone is looking for a master's thesis, for sure this is a good one. Okay, so that solves the problem of scaled matching in one dimension by truncation. And as I said, you can think about it if you want as kind of an exercise, which I'm not going to go back and do. It's easy enough. But you can think about it how you change it a bit in order to deal with rounding. It all works. Yeah. 1 second. I move away from the air conditioning. When I'm saying here compressed text, it's I wrote run length compressed text. Now, run length compression, so let me say something about compressions. So when you say compression, there are all kinds of compressions out there. So for text, a lot of people use gzip, which is based on Lempo-Ziv compression. And you may have seen it or not. I don't know, but that's one known compression. And the nice thing about the LZ, the Lempo-Ziv compression, is that it actually is provable. It reaches the entropy, and that's what you prove. So it compresses up to the entropy. Now, another entropy compression, but not as good because it's the entropy of the characters rather than of the entire thing, is the Hoffman compression. So Hoffman compression also is an entropy compression. But there's something called the run length compression. Run length compression is the compression that fax machines use because the original faxes were basically black and white. So what you had is these rows of black, 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 white, white, black, black, black. So the way that fax transmitted was it would take the run length of the blacks. So there were 356 blacks, so it would go 356. Then there's a lot of white pixels. So there is like 3,000 white pixels and so on. So this is called run length compression. It's a compression of that's based on the run length. This is not an entropy compression, but it's good for some particular. It's easy to it's easy to to do pattern matching in run length compression because to do exact matching is very easy since you're not stuck in the middle of anything. In Lempo-Ziv compression, for example, if you're looking for something and your something starts in the middle of one block and ends in the middle of another, you have some sort of a problem. Even in Huffman compression, these are all compressions where you don't know where you start and where you end. Run length compression is easy because you can just and there's another problem with these compressions that I'm talking about, not just where it starts and where it finishes, but you cannot always compress the text and compress the pattern and look for the compressed pattern in the text. If you look at Lempo-Ziv, it's an adaptive compression in the sense that it adapts. So the text itself may be compressed differently from the pattern. So you can't just compress the pattern and say, fine, find my pattern in my text. In Huffman compression, it is not adaptive in that sense, but you don't know where it starts. So if you're saying, well, I know that what I'm looking for appears here, you still need to start all the way from the beginning because you don't know where is the beginning of every one of your blocks in the Huffman compression. But in Lempo-Ziv, it is totally unadaptive. So it's a big problem. Run length compression is very nice. It's completely adaptive. Compress the text, compress the pattern, you do exact matching by KMP, and it's linear in the compressed size. So what we did at some point, we actually looked at run length compression, but in 2D, because that presents problems in and of itself, since, yes, finding an exact match in every row is easy, but what happens when you need to align the rows, and at that point, your alignment is completely off, and how do you do that fast? So we also looked at all kinds of compressions where how do you do a search for a pattern without, as it were, uncompressing. So if you have a whole lot of files in the memory and they're compressed and you're looking for something, then you don't want to really uncompress and look and then compress again. Can you actually find the compressed stuff? So there were a lot of challenges in it, both 1 and 2 dimensions, and there was a lot of work that was done. In fact, we started this trend and it became a huge field that a lot of people work in. However, as I said, run length compression is very easy when you do exact matching in a string. And you do it in time the size of the compression. The time is O of the size of the compression, not O of the size of the uncompressed text. In some sense, what we did here is we showed that by compressing, you can save time. So you can compress the text, and now your time is going to be still linear in the uncompressed text, but what you really are working with are compressed texts. It could be conceivably that the run length compression was very, very good, and so our very long text is now very short, and the very long pattern is very short. So what it says here is, let's see if we can have an algorithm that does the scaled matching, but in the compressed text without uncompressing. So you want to be linear in the size of the compressed text, not linear in the size of the uncompressed text. So that is the question that I'm saying is open, and we don't know what to do with. Okay. Any other questions on this? All right. So now that we even have an open problem. So you got a bunch of open problems. I expect that by the time I go to Israel, 2 or 3 people will get their masters. So now the question is, what we want to do is solve parameterized matching, but with don't cares. So we have a text with don't cares. We have a pattern with don't cares. And we want to do parameterized matching. How do we do it? Okay, so let's skip all the parts of this that talk about what parameterized matching is, because we know And let's just look at the parameterized matching with don't cares. We can make this smaller, of course. Now, the point is this. Again, as I always told you, when you are presented with a problem, think of the naive algorithm. In our case, it's not so naive, but it's naive in the sense, what can we do fast with the tools that we have? Now, we hear don't cares, so right away in our brain, ding, 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 convolutions, we're going to do FFTs, okay? So we want to do FFTs. The second thing that we know is that when we're doing FFTs, we said, although we have used it in different ways, but one of the powerful ways in string matching to look at FFTs is the fact that you can very quickly match binary strings and count all the clashes of ones and shift, and in time n log n, know for every place how many ones clashed for every shift, which is what the FFT knows how to do. And I bet it wants an Adobe Reader, right? Yes. Adobe. Okay. So having said all that, so the naive, or not the naive, or the straightforward algorithm that we would do is going to go in time O of square root of n times n log m. Why? Because what we're doing here is we're taking the pattern and we want to do a parameterized matching of the pattern and the text. Now, what does that mean? It means that if I have A's in the pattern and B's in the text, and I match the A's to the B's, then I want all the A's in the pattern to match all the B's in the text. So if let's assume that we have a small alphabet, and now we're talking about fixed alphabets, because what I'm going to show you does not work for unlimited alphabets. But let's assume that we now have a fixed size alphabet, and the size is, let's say it's 4, because we're talking about DNA or something like that, or RNA. Okay, so we have a fixed alphabet. Now, what does it mean when I'm saying parameterized matching? So I want to see, for every shift, let's see if A actually matches B. So let's look at all the places where A matches B. A in the pattern matches B in the text. Now, let's also look at all the places where A in the pattern matches C in the text, and all the places where A in the pattern matches D in the text. So we have A, B, C, D. So we'll do all of these FFTs for A in the pattern and B in the text, A in the pattern and C in the text, A in the pattern and D in the text. Each one of them, we know how to do in n log m using the convolution. So because that's this smack binary thing, right? Because we're going to look at chi A of the pattern times chi A of the text. That's going to count all the places that A matches A. Then we do chi A of the pattern, chi B of the text, and it counts all those times, and so on. So if we're going to do this for every pair, A and B, every pair in the pattern and every pair in the text, so we're going to end up with O of sigma squared times n log m convolutions. But does that help us? Yes, because at the end, we actually write down, since our work was sigma squared times n log m, well, we can afford afterwards to sigma squared times n work, right? So put for every text location, every one of the text locations, write down which one of these sigma squares we actually found and how many I found from each of them. And if for any one of these locations I found that I have an AB and also an AC in that same location, there's no parameterized match. If I found an AC and I found a BC, then also there's no parameterized match. So what we're allowed to have is only these pairs AB, such that there are no repetitions in the A and no repetitions in the B. In some sense, it's like a bipartite matching of these things. So, so that's what we want. So, and that's the naive algorithm, and its time is O of sigma squared n log n. So for every pair, A and B in sigma, that's what we're going to do, chi AT times chi AB. And we're recording the pairs of all the non-zero results in every location. So that's what we're going to do. And then, of course, the time is O of sigma squared n log m. And then we're going to sort those pairs by the first, then by the second element. And the sorting can be done in n times sigma squared log sigma, but in fact it can be done faster because we can radix sort this thing. So we can even sort in sigma squared time for location. So for every location, we can sort these things in time O of sigma squared times n. And then for every location, after they're sorted, it's easy for us to check whether at most one pair AB exists for every A in sigma, and at most one pair AB exists for every B in sigma. That's a parameterized match. Everything else is not a parameterized match. So this is an algorithm that we know how to do. And for example, if this class had a test, God forbid, then this would be like a beautiful question that one should know how to answer in a test. I even asked this question once in a test in an algorithms class where they learned how to use FFTs in string matching, and then so this was given as a test question, and people did very well because this is the kind of thing we know how to do. But what I'm going to show you now in the remaining half hour that we have until we all go and celebrate is that is a result of Wei Min Chen from 1999 that says, but I can do better than the test. I can do it in time O of sigma times n log m and not sigma squared. Now, Wei Min Chen's algorithm, in some sense, is also, it uses convolutions, and he uses it very well because there are a lot of things that need to be done, and he does it with a convolution, and everything's good, except that in itself is not enough, but he also needed a number theory proof in order to get a property that is going to allow him to work faster. So what we see here is that sometimes for an efficient algorithm, sometimes you need the tool, the algorithmic tool like FFT in this case. But like we saw in the last example, what you need is some other property. So we actually used pigeonhole in order to count, the pigeonhole principle in some sense, implicitly, in order to count how many parameterized matches we have. And that got us a faster algorithm. And we used before already number theoretic ideas. So here also, he has a number theoretic lemma, and that one is going to do it. It's going to help him get rid of one sigma in this case. So he's saying the following. Suppose that I have a bunch of integers, a1 through ak. Then he says that it's always the case that the sum of these k integers squared, so add them all up and square, it's going to be less than k times the square, the sum of the squares. So that is always the case. And the equality holds if and only if all of them are equal. If all the numbers are equal, then in fact the sum of the k numbers squared is equal to k times the sum of the squares. But it's always the case that the square of the sums is less than or equal to k times the sum of the squares. Now, first of all, you ask yourself, why think about this? This is crazy. What prompted him? What was he on drugs? Why was he thinking about this problem at all? But the point is this. He knows, Wei Min Chen, and we also, we know how to do a lot of stuff fast with convolutions. In particular, we know how to add things real fast. Now, when you are, and also, what is it that we're adding? Remember what we're adding. We're adding all the places where the ones clash, okay? So now, suppose that the ones are going to be a symbol in the pattern. Okay, so the pattern has sigma symbols. So we're going to take the pattern and we're going to do chi of some symbol in the pattern. So that's what gives us the one. So chi sigma of the pattern. But what happens if I multiply this by the entire text? Not by chi sigma of the text, which is what gave us the sigma squared. So I just multiplied by the text as is. Well, then I'm going to get a whole sum of numbers. But I want to know if these numbers are the same number or not. And I want to know that fast. So he says, okay. So here is something that if these numbers, A1, A2 through AK, are the numbers that actually juxtapose the ones in the chi sigma. So I'm doing a chi sigma and I multiply. I want to know that all these numbers are the same. Okay, so here's a way of knowing it. Let's look for all these numbers square. Let's look for the sum of the square of these numbers. Let's multiply it by k. And if it's equal, then they're the same. And if it's not equal, they're not the same, and I don't have a parameterized match. But if they're the same, then maybe it's a parameterized match, because this number in the pattern matches the same number in the text everywhere. So that's what prompted Wei Min Chen to actually look at this, because he was looking at some way of getting a sum of numbers and knowing if they're all the same or not. So that's what he was aiming for. So it's not that. So another thing I'm trying to do here is to tell you the difference between an algorithm that you see in a paper and how you think about an algorithm. Because when you see an algorithm in a paper, the idea is to make you as mystified as you can so that the paper can be thought of as hard as it can be thought of and be accepted to as powerful a conference or as a prestigious a journal as possible. So if you cannot make it seem totally unbelievable, then you're not going to get into the really good journals. So therefore, they take the bottom line and they spring on you all kinds of these weird lemmas, and at the end it all works and you say, wow, this is very hard. But obviously, this is not how you think when you do research. And what's important for me is that you guys understand how to do good research. And so the idea how to do good research is you're looking at the problem and you have some tools. Say, what bothers me from using these tools? What property, if I had, I could use these tools that I had? And then you say, okay, I'll try this and that and that. And if some property does help, then all of a sudden. But at that point, when you present it, you go backwards and you just present the property as if it came down from heaven by some angels wielding powerful swords. And so it looks very exciting. Now, in fact, let me also say something else. Another thing, because of this, personally, I love algorithms that end up being simple. If there's a problem, and all of a sudden some simple observation gives a simple solution, I love it. The problem is that when I'm a reviewer for a conference, or when other people are reviewers for conference, and we are presented, we get a paper and we read it, and if it's very simple, very often the reviewer tends to say, well, it's a simple solution, it is not up to par with the level of the conference, and so let him send it to some Mickey Mouse conference. So people would tend to do that. But then I say, well, something is wrong, because if there's a problem that's hard and there's a very nice solution, then that should be considered. Which is why, and I recommend this to everyone who is ever reviewing a paper. When you're reviewing a paper, don't start by reading the paper. Start by reading what is the problem that the person is trying to solve, and then don't read how he does it, and think about it for not long, half an hour, okay? Think about it for half an hour. What that is going to allow you to do is, if it's really a trivial thing, you'll figure out the answer, and then I don't have any problem saying this is easy. I thought about it for a few minutes. I came up with a solution. This is not a hard one. But what generally is going to happen is you think about it for half an hour, and you get stuck in all kinds of corners, but you realize where are the difficulties here in the problem. Where is it in this half hour you got stuck? So don't think more because the problem has already been solved. But in this half hour, it's enough to actually tell you where you're stuck. And now read the paper. And then all of a sudden you see, wow, this is how I got unstuck, and it's so simple. How come I didn't see that? But it gives you the appreciation. Because although it's simple, it's not obvious. And there's a difference between simple and obvious. And at that point, I have found myself a couple of times accepting a paper even though the solution does not have any big tricks or any hard math, or they don't use vector analysis and homological algebra. Nevertheless, because they managed to, in such a simple way, overcome a problem that I encountered while thinking about it, I said, okay, I love it. So this is what I'm saying. So now here, if I just told you here's a lemma and then showed you how the lemma worked, you would say, wow. But the fact is that when you're thinking about the problem, you'll say to yourself, okay, instead of sigma squared convolutions, if I have sigma convolutions, it means that one of the sides, either the pattern or the text, I'm going to actually do a convolution for every symbol sigma, but in the other side, I'm not doing it. So if in the other side I'm not doing it, then I'm actually multiplying numbers, not ones and zeros. And if I'm actually multiplying numbers, I need to know if they're the same or not. That's where the lemma comes in. All right, so what does the lemma tells us? That there is an easy way of deciding whether a bunch of random numbers are different or not, and that way can be done without looking at all of these numbers and saying whether they're all the same number, but rather by doing some sort of a arithmetic operation. In this arithmetic operation, at least summing things fast, we know how to do on a shift by the convolution. Okay, so in order to prove it, we need the following claim. Let's move it up. So we need the following claim. For any two integers, 2ab is less than or equal to a squared plus b squared. And in fact, if a is equal to b, then 2ab is equal to a squared plus b squared. So for the equal part, we don't really need to think too much, because if they're equal, then it's 2a squared, and a squared is equal to b squared. So yeah, so if they're equal, it's fine. I know, but if they're not equal, it's actually strictly less. So let's prove it. And it's an easy proof. Without loss of generality, let's assume that b is greater than or equal to a, so b is a plus x. Now, in fact, this proof proves everything, because if x is 0, then b is equal to a. But in general, if b is greater than or equal to a, so b is equal to a plus x. So 2ab is 2a times a plus x, which is 2a squared plus 2ax, and that's less than or equal to 2a squared plus 2ax plus x squared, because I added something. But in fact, if they're equal, then I didn't add anything, so it's strictly equal. It's not less than. So it's less than if the numbers are different, and it's equal if they're not. Okay, but now that we have this, we can break it up, because this is actually equal to a squared plus a plus x squared, which is equal to a squared plus b squared. So we have equality all the way, except for here where there's an inequality, and this inequality is an equality if and only if a is equal to b. So that proves this claim. Okay, little claim, 2ab less than or equal to a squared plus b squared. So now we can do an induction on k and prove the general case. And so the general case, remember, is that the square of a sum is less than or equal to k times the sum of the squares, where there is equality if and only if all numbers are the same. K equals 1 is almost not need to write, because the square of the sum is really the square of the number, which is of course less than or equal to 1 times the number. So yeah, all right. So let's now assume and the equality holds when all elements are equal, which is also null. Okay. So now let's now assume the inductive hypothesis, which is that the sum of all the numbers squared, the sum of k numbers squared, is less than or equal to k times the sum of the squares, and equality holds if they're equal. And we need to prove this for k plus 1 numbers. And now, by the way, like I told you, induction is used for proving things on natural numbers, and this is how you do it. Because if it's true for k, now it's going to be true in general for all the numbers. So that's where induction is really powerful for proving things on natural numbers. My number theory teacher, Professor Muscat, used to prove by induction that all the natural numbers are exciting, that they're all interesting, that all the natural numbers are interesting. He said, okay, let's prove this by induction. Well, 1 is interesting. Obviously, it's interesting. It's the smallest natural number, so it's got to be interesting. So, okay, inductive hypothesis. Let's assume that all the numbers 1 through k are interesting. And now we need to prove that number k plus 1 is also interesting. Well, assume to the contrary that it's not. Well, then what do you know? K plus 1 is the smallest uninteresting number. Now, the smallest uninteresting number, that's an interesting thing to know. Of all the uninteresting number, he's the smallest. That makes him interesting. So that contradicts the assumption, which means that we have just proven by induction that all natural numbers are interesting. So I studied number theory with him, and so I started loving all the numbers by induction. They're all interesting, so you gotta love it. All right, so and it's a good proof, by the way. I mean, there's nothing wrong here with the inductive hypothesis. Okay, so we now need to prove that the sum, where I goes from 1 to k plus 1 of ai squared, is less than or equal to k plus 1 times the sum of the squares of the ai's up to k. And if they're all equal, it's equal. All right, so we're starting, and this is going to be like this boring type of opening and closing and moving and distributivity. And okay, so the sum of ai squared is equal to the sum of ai. The sum to k plus 1 is equal to the sum of all the numbers till k plus ak plus 1. So I didn't do anything. I just took it out of the sum, and I square all of that. However, once you do that, you can already break up this summation. So that's equal to this sum squared plus this sum squared plus 2 times ab. And this is where we're going to use that little factoid that we did together, that we did before about the 2ab, okay? So here I didn't do anything. And here, what we really have is, let's move this 2 inside, and let's move the ak plus 1 inside. So this is equal to that. Okay? And now we're using that little claim of ours. So here we have still not done anything, but this 2 times ai k plus 1 is actually less than or equal, and if they're all equal, it's equal to ai squared plus ak plus 1 squared. Okay? So good. Let's move on with that little list. And this is equal to the sum of this and this we haven't done anything with, but this is equal to k. Where are we? We're here. This is equal to k times ak plus 1, because it appears here in the sum k times. So it's k times this plus the sum of these guys. All right. So far we've been using distributivity all the time, but we're here. And now we can use the inductive hypothesis. So the sum of ai squared, where do we use? No, the sum, this sum. The sum of all the ai's squared is less than or equal to k times the sum of the squares. So this is all less than or equal to k times the sum of the squares. So k times the sum of the squares plus, I think I still need the one on top to see what came down here. Yes. Plus the sum of ai squared here. This came from here. Plus k plus 1 times ak plus 1. So we're gathering these things together using commutativity and distributivity. Gathered all of them together. So what do we have here? We have k plus 1 times this, ai squared, plus k plus 1 times ak squared. But now we can stick the ak plus 1 squared inside. So we have k plus 1 times the sum of the squares. And that's the end. I mean, that's where we wanted to get. So we started out with the sum of ai up to k plus 1 squared, and we ended up at the end of all of this with that it's less than or equal to k plus 1 times the sum I goes from 1 to k plus 1 of ai squared. That's what we wanted for the inductive hypothesis. And also, inductively, all of these less than or equals along the way, every time there was a less than or equal, if they were all equal, it was equal. So the inductive hypothesis holds all the way, and k plus 1 has been proven. All right, so we are ready now to conclude. So the lemma is going to be used for the following algorithm. The first thing you're going to do is you're going to replace the text alphabet, whatever alphabet it was, because we're talking here about parameterized matching with don't cares, not about numbers. And we're going to now use numbers. So you have to replace the text by numbers. And the numbers we're going to use is 1 through sigma t. But in time, n log n, you can do that. And here, you're going to have a bunch of n log n's. So fine. Even n log m, you can do it because you can assume that the text is of size 2n. So time n log m, that's what we're going to be talking about here. All right, so we replace the text alphabet by 1 through sigma t. And now, we're going to want at every location and for every sigma in the pattern to be able to check whether k times the square of the sums is equal to, whether the square of the sums is less than or equal to k times the sum of the squares. So we're going to need to get the squares. To get the, we're going to need to get the sums, and we're going to need to get k. Now, even to get k is not entirely simple. Why? I mean, what's k? I'm taking a sigma in the pattern, and I want to find out all the numbers that match sigma, okay? But sigma, I know how many times sigma in the small sigma, a, let's say. I know how many times a in the pattern appears. So a appears 5 times in the pattern, so k is equal to 5. No? No, because we're talking about pattern matching with don't cares. So it could be that in this particular case, not 5 elements in the text matched a in the pattern, but only 2. The others were don't cares. And don't cares are certainly going to be a different number than whatever text I'm looking at. So the don't cares are a different number. So we have to discount the don't cares. Somehow the don't cares are going to be 0, so I don't get them. And so the numbers I get that are opposite a in the pattern are going to be just the numbers that are not don't cares. And so I need to know how many numbers are not don't cares. So the k is also something that I need to know. Now, but why did I say this is a tour de force of convolutions? Because you can know that by convolutions also, right? How? How can I know the k by convolutions? So I have a in the pattern. I want to know how many elements in the text match those A's that are not don't cares. Okay, take all the elements in the text and change them to ones. The don't cares are don't cares. I mean, they're always zeros. When you do a convolution now, what are you going to know? You're going to get a clash of all the of chi A of the pattern. So you get a clash of all the places in the pattern that were A, and there was also a 1 on the other side. That's K. That's the K that you want. Because for every shift, it may be a different number, but for every shift, you know what it is. So you write down for every A, so for every pattern element, you write down what is the K of that element. That is still sigma times n. Okay? So sigma times n. First, you need to find out how many elements you have in front of you in order to get the K. The second thing you need to do is to find out for every such sigma, what's the square of the numbers in front of it. Now that's very easy because to know the numbers in front of it, that's a regular convolution. Take the text, multiply it by chi A of the pattern, and if you multiply the text by chi A of the pattern, what you're going to get is exactly the dot product of all the ones where there's an A in the pattern and whatever there was in the text. So it's going to add all the text elements that match the A in the pattern. It adds up all of them. You do that in a convolution, you get it for every location. You square it, you get the sum of the elements squared. So now you know the sum of the elements squared, and you know the K, and so you get the sum of the elements squared. It has to be less than or equal to K times the sum of square of the elements. How do I get the sum of square of the elements? Another convolution. This time, take the entire text and raise it and square it. Every element, take it, multiply it by itself. Now you have the squares. When you do a convolution against chi A of the pattern, what you're getting is the sum of the squares. Now you got everything. So ask whether the sum of the elements squared is equal to K times the sum of the squares. If it's equal, it's a match. If it's not equal, it's not a match. Okay, so if the idea is clear, let's follow now the details. So first of all, let's write an array T squared. The array T squared is going to be an array where every position in T squared I is really Ti squared. That's going to be that's what we'll use to do the convolution that finds the sum of the squares. So we now define the T squared. Now, for every sigma in sigma P, we do the following. Multiply T times chi sigma, that's the alphabet symbol of P. And you put that in M. What that does for you is adds up all the numbers that match sigma. So you added them all up, you put it in M. In Q, you're going to put T squared times chi sigma of P. Now you have the sum of the squares. As we said, we need to find out what K is. So K is going to be the following. T prime is going to be the array where T prime is 1 if the number is not a don't care, and 0 if it is a don't care. So T prime times chi sigma is going to give us exactly the K. Those are the numbers, the real numbers that I actually count for this particular location. Now, K times Q is going to be K times Q in the 1-by-1 multiplication. So K times Q, Q was T squared, so that's K times the sum of the squares. So you do all these. How many convolutions have we done? 3 convolutions per symbol in sigma, per sigma symbol in the alphabet. So our total number of convolutions is only sigma times, our total number of convolutions is only sigma, so our complexity is sigma times n log m. Okay, as we had mentioned, mi squared is the sum of ai squared. Kqi is k times the sum of the squares. So wherever the AIs are all the same, then that text number matches sigma. So, but we're not done. Why aren't we done? Because what we have established so far is every location where kqi is equal to mi squared, it means that all the text numbers that match sigma are the same. But it's still not a bijection, because it could be that all the text numbers that matches A are the same, and all the text numbers that match B are the same, but they're the same for A and B, so it's not a bijection. So we need to check that. But that's already an easy check, because what it means, okay, so it could be that some text number matches 2 or more sigmas. But that's an easy thing to find out, because for every sigma, you record the unique text number that matches it. I mean, we did it sigma times anyway, so run through every location, do qi divided by ki, for example, and at that point you will know what is the text number that matched this sigma, because this is the number of times it was, and this is the sum of them. So, okay, so that's one way. There are other ways you can find it. But in time O of 1, you can find what is the unique text number that matches sigma. And now you just need to find out that all of them are different from each other for every location. So a location is a parameterized match with don't cares if and only if all the text numbers are distinct. Now, again, that's easy to do in n log m times sigma time, because this is the element distinctness problem, right? We know we can do it in n log m time. So that solves Wei-Min Chen's problem. And that shows how we can do pattern matching, parameterized matching with don't cares, with a bunch of convolutions. The use here of convolutions is good. It's very pedagogical, because you really see sometimes it's 1 times 1, sometimes binary. Sometimes you want to add the numbers, and you can gain by adding them. But the idea that you can actually do a dot product, shift, do a dot product, shift, do a dot product, time n log m, that's the idea that the convolution gives us, and that's the idea that was used here. Okay, so we're going to stop here for today. What we're going to do tomorrow is we're going back to two-dimensional matching. We're going to do rotations, because, like I said, we want to get to indexing at some point also. So we're going to do rotations, and we're going to start indexing. So that's the plan for tomorrow.